Okay, here's my design schematic for the battery eliminator for the IM-25. It's designed to replace both the 3-volt battery and the special 1.35 volt mercury battery. I start out with a transformer, power transformer of 1.1 VA, and I chose a Signal brand split bobbin transformer model ST-2-12, which is really a 12.6 volt secondary if you count both secondaries together. These can be wired as separate secondaries like I show them here, or you can connect this point to this point and treat it like a center tapped 12.6 volt secondary. Because I need two isolated supplies here, I'm using them as totally separated secondaries, and they're galvanically isolated one from another. There's no circuit commonality here. To the degree that they get connected together, that will be done in the meter, not here in the power supply. The primary is a single winding set up for 120 volts AC nominal. There's another version of this transformer which has a dual secondary which can be wired for 120 volts or 240 volts, but in my situation the rest of the meter isn't designed. Well, I take that back. The IM-25 could be set up to run off at 240 volts, but since it's not wired that way on the one I have, I'm just going with the simple primary here. I'm using full wave bridge rectification. Oh, I should point out that the secondaries are 6.3 volts each at about 100 milliamps max. You don't want to pull much more than that from them, and I shouldn't have to pull anywhere near that much. This is very oversized. I've got, per my calculations, to get as clean a power supply as practical here, I've got a dual 470 microfarad capacitor, two of them in parallel. My calculations said that I should have ideally an 830 microfarad capacitor, so this is more than that. But without going crazy, I didn't put in 1000 microfarad, for example. And the reason I have it split into two capacitors is A, because most manufacturers don't make anything close to 830 microfarads, and also I wanted to, in order to keep the circuit board small, I wanted to use two smaller capacitors that I could arrange in any position that might be needed to minimize board space, where if I used one can, it would limit my options. And I'm using an LM317T. That's a adjustable linear voltage regulator IC. Quite a classic. The adjust pin is connected to the output pin with a fixed resistor. This resistor can be anywhere in the 220 to 240 ohm range, according to National Semiconductor's data sheet, and they're the ones who originated this chip. 220 is a more common value than 240, so that's what I used. And you're trying to draw out a current which I'm calling I adjust here, and that current is impressed across this resistor here. Basically it's a loop, and you want to end up with about 1.25 volts across it. In fact, the IC will adjust its output to get 1.25 volts across it. To rephrase that, you've got current coming out of the output that is coming down through this resistor voltage divider, and you also have current coming out of the I adjust pin, which joins that current through this part of the divider. and the IC is always trying to adjust its output to get 1.25 volts across this resistance. And if you just do the math on it, it ends up being that you need a certain resistance down here to satisfy that criteria. There is also, since this is a voltage divider here, it's common practice to hang a stabilizing capacitor across the lower element, and that's also recommended by National Semiconductor in their data sheet. So I have a 10 microfarad capacitor here. I've got 100 volts listed because once the capacitance values get small like this, 100 volts is often about the smallest voltage you can get. If they made it any smaller, the part would be ridiculously small, so they just kind of start around 100 volts and go up. Anyway, the formula for the output voltage is 1.25 volts times whatever's in this bracket, which is the R adjust resistor plus the fixed 280 ohm resistor I have here, and that is divided by the resistance here, 220 ohms, and then that's added to a constant of 1. If you do the math here, assuming that this 50 ohm 10 turn trim pot is initially set to about 28 ohms, it works out where you should get 3 volts out of the circuit. So this would replace the 3 volt battery. And then a very similar circuit here for the battery eliminator for the 1.35 volt mercury cell. Same circuit really. It starts with another 6.3 volt secondary full wave bridge rectification. In this case I only need, well, you don't even need this much according to the calculations and the very low current drawn, but I opted for putting another 470 microfarad capacitor as the filter, just since I was buying some to use up here. I use the same value. And I'm going to lay out the circuit board to have holes for an additional one. I don't think I'll need it, but I'm going to have that. And I have the same 220 ohm resistor here, but I do not have the extra 280 ohm resistor like I did here. The value of this resistance here to here is essentially what's dictating the output voltage, and the higher the resistance here, the higher the voltage. Since I'm trying to dial this down to only 1.35 volts, all I have is the trim pot. It's another 50 ohm trim pot, and it's going to be set to about 17.6 ohms. And doing the math, it's R adjust, which we're calling 17.6 ohms, divided by 220 ohms, and the result of that added to 1, and the result of that multiplied by 1.25 volts, and that comes out to 1.35 volts as the output of the circuit. In addition to that, I'm just following good practice here and putting a backwards facing diode across the output to input terminals of the regulator. And that is because these are self-protecting, current limiting, temperature compensating, everything ICs, but the one thing they have no protection for is if you have a higher voltage applied to the output than there is on the input. So if I accidentally, for example, connected up the leads here wrong, or some other screwy thing happened in the circuit out here that resulted in more voltage here than this part of the circuit is trying to put here, then you could reverse bias this and it would snuff this IC out pretty quickly. So you put that diode there, so in that case the current can bypass it and not do it any damage. In this meter application, I think there's a slim chance of needing those diodes, but I'm putting them in anyway. I just did a quick pencil and paper sketch of how I might lay out the circuit board with the transformer here, holes for the AC voltage coming in, 2 diode bridges. Instead of using 4 discrete diodes, I'm going to use a diode bridge package in a dip package. The current is very low, and these are actually good for up to 1 amp, but I'm going to be using them at a tiny fraction of that. And then I'll have the 2 electrolytics in parallel, and then another one for the lower voltage supply with a space for an optional one here. I've got the 220 ohm resistors here. I've got the backwards facing protection diodes. I have the LM317s here with a small heat sink. I have the stabilizing capacitor down here. I have the trim pot here. And in the case of the higher voltage supply, I have a position for the 280 ohm fixed resistor. I'm going to probably lay out the board the same way and just put a jumper here, and that's as a contingency in case I want to use this board design for some other power supply in the future. Once I lay it out on the computer, by stuffing another resistor in here instead of a jumper, I could turn this into some other supply. So this is really just here to salvage the circuit board design in case I want to reuse it for something else. And then finally, circuit board positions for wires going out to where the 3-volt battery would be, and for the 1.35 volt battery. Now I have to work out the exact dimensions of the circuit board I'm going to need and make sure it will fit inside the space available in the meter. And I have a whole stack of these fiberglass copper-clad blank circuit boards, and even though this is drawn not to scale, it's not too horribly far off of scale. And as a proof of concept, I can already see that this board will be plenty big enough, and I can fit it in the space available on the meter, but I'm going to try to make it even smaller. I'm going to minimize the space it takes up once I actually start seeing things drawn to scale. And I have over here, I got my DigiKey order in. I've got my Bourne's trim pots. Again, I'm buying enough parts here to make the battery eliminator for all 3 of my IM-25s. The one I've just restored, and the other 2 I have waiting in the wings. I've got the bridge rectifiers. It's kind of hard to see them, but they're in there. There's the LM317s, 6 of them. Here are the 280 ohm resistors and the 220 ohm resistors. The heat sinks, I bought 6 of them there. The 470 microfarad capacitors. The 10 microfarad capacitors. And a bag of 3 power transformers. Alright, I've reverted to my old habits and used my very old school Bishop Graphics templates, which are designed for double-sided circuit board artwork. There's another one. Has all the different shapes and pad layouts and things. And a circle template. This is not doing it via CAD, although I could have. I just had more fun doing it this way. So the available circuit board area was this big here. And I wanted to make it a bit smaller without really crowding things. I left a generous area on the end for a spacer, probably a 440 size, to support one end of the board and something similar at the other end. I put my power transformer here. I have a bridge rectifier and 2 filter capacitors on each side for the 2 supplies. And it's not a mirror image, although this part is like a mirror image almost. But then you just have the same components here. Resistor, diode, LM317T voltage regulator with heatsink, another capacitor, trim pot, another resistor, and then the pads for the DC output, and the same thing over here. So that's a nice open layout. It's a little more crowded here. I actually thought I might be able to jam all these parts in sideways and have the board only be about this tall from here to here, but it wasn't going to happen. So then I just said, yeah, go ahead and leave some room around the heat sinks for more air circulation. I don't think they're even going to get remotely warm, but just good practice. I like to leave a little space around them, so this area is deliberately kept open. No components up really close to the regulator chip. And that should work out pretty well, I think. And then I did a nice hand layout job. Marked it up with red pen so I can see from the component side what the foils will look like. Nice easy routing. And I will lay this out in the only software I have that does circuit board layouts, at least for the actual foils, is the Express PCB free software, which works fine for boards that I do. The downside is that they don't let you generate Gerber files, so you have to use their service to get the boards made. But I'm not going to use their service in this instance. I'm going to print out a 1-to-1 or full scale layout of the board with showing the foils, and then I'm going to try to use it with a thermal transfer of the toner to the circuit board and see if I can get that to work. I've only had spotty results with that before, but I've recently acquired a heat press, and that might make the difference. I also did a quick study on clearances. There's approximately 1.5 inches between the inside of the rear panel of the meter and the back side of the meter circuit board. So 1.5 inches between those, and assuming I'm using 1/4 inch standoffs between the back panel or the rear panel and the back side of the battery eliminator circuit board, and the circuit board is 1/16 of an inch thick, and you've got the transformer and heat sinks drawn to scale and position, there's approximately a 1/4 inch clearance between the top of the transformer and the rear of the circuit board. And I'm going to be positioning it so it's more or less behind the power transformer for the meter that's up in this same area, and there will be nothing, you know, if there's any stray magnetic fields here, it's not very close to anything on the circuit board that would even remotely care about that. Certainly no more than it cares about anything radiating magnetically from the transformer that's already there up in this same area. So it should be good. Can you hear all the banging around out there? Tomorrow's the 4th of July and everybody's setting off their fireworks early. Anyway, so this is where the power transformer goes normally, and there's really nothing in this area except, or even this area, of any great importance. So as long as I keep the transformer over in this area, it should be right behind this one. And I could move the old battery pack, but I want to leave everything in here that was original. This is an actual size printout of the circuit board layout, and it's going to be mounted from the 2 holes. So it'll probably go can't go down too far or it'll come too close to these guys, but I think right about there would be good. I wouldn't even have to move the Heathkit sticker if I don't want to. I could leave it there, but I think I may see if I can lift it up with a razor blade and transplant it over here or over here. But I think this is where this guy's going to go. So I'm starting out in Express PCB's design software. Created an outline of my board, set to the correct dimensions. Next I want to place all the pads, and in this software you can drag them into position or you can position them with the X and Y coordinates, assuming that X of 0 and Y of 0 is the upper left corner. So I've already gone through and when I laid it out I tried to line things up quite a lot, so I've got my X and Y dimensioned marks on my sketch of the board. And I've toggled on and off. I don't want to look at the red layer, which is the component side foil layer, because this is a single-sided board. I do have the silkscreen layer turned on, although actually I don't need that. I'm not going to do a silkscreen here. Oops, there we go. All I have is the bottom copper layer turned on. I drop my first pad on the board. It's just an arbitrary size. In the dialog box I select a 1/4 inch round pad with an 1/8 of an inch hole. That's going to be for one of the mounting holes. And I give it its X and Y position. And if I click OK, it materializes there. If I click off of it, it becomes green, which is the color of the or the foil side or back side traces. Mounting pads are in place. And then the holes for the wiring. I may actually make these a little larger. One limitation of this free software is that you can't just have any pad size with any hole size. It has a limited number of selections. I don't know, it's like 50 or 70 different predefined pad and hole sizes, and you can't change them. So if you want a pad of a certain size, once the pad gets larger, and you might want that for mechanical strength or something, it's going to make the hole a lot larger. Not that it's drilling the hole, but it also affects the pattern, and you may end up with a lot less copper in the middle of the pad than you want for the hole you intend to drill. Alright, I've placed the patterns for the dip diode bridges, the voltage regulators, and the trim pots. I had lied a little bit before, or was just remembering the way it used to be when I used this software years ago. They do now allow you to create custom pads. So these ones I had for the wiring, I was able to create new pads that were larger in diameter but had smaller holes in them, and then I used the same pad for the power transformer, and also replace these guys down here. So that's an improvement. Okay, I've located all the pads on the board layout, and I've changed the software settings so it displays the foil side, in other words the anti-component side, in red instead of green, because that's more the way I'm used to doing it. And I've also added all sorts of helpful text, plus signs next to plus signs of diodes and capacitors, and a K next to the cathode, following the K instead of C convention in that regard for the diode. I could have made a diode symbol, but the way the trace is going, the symbol would have been a lot larger and it wouldn't have fit very well. I've got 120 volt AC up here by the input terminals, I've got 3 volts and 1.35 volts. I've got adjust and input orientation next to the voltage regulator pins. And everything is backwards, of course, because when viewed from the other side, viewed from the foil side, they're going to look correct. And the software does that automatically because it knows it's the foil side or the anti-component side. And then on the left I've got Heathkit IM-25 solid state VOM, 3 volt and 1.35 volt battery eliminator, and then my initials and the date. Just normal circuit board layout practice. Okay, I've completed my layout and double checked it. Okay, I've done a full size or actual size printout. The software wants to slightly gray the area within the board outlines. I don't think that'll be enough to cause any problem as etch resist. It should be too thin to even count. So I'm just doing a couple sanity checks here. This should be 2 3/8 inch wide. If I can manipulate my ruler. 2 3/8 inches wide. And it should be 3.5 inches tall. Do a few things like imaginary lay the voltage regulator on its pins, the trim pot, the diode bridge. Well, the capacitors should be okay that way. If I line up a couple of them on the center lines approximately, verify that they should fit. Right on the money. And now I have to envision gluing this up or affixing it to the back of the circuit board. So it should look like this from the back. And the text should come out looking correct. I don't think I've screwed up on the polarities of anything. Things like diodes and capacitors can simply be reversed. And this is a view from the front of the board. And I know that the plus is at the lower left there, so that agrees with the layout here. And I know these pins are adjust out in from left to right. So if I put them with it flipped around that way, it's adjust out in. A and in are identified on the board. The transformer doesn't care about polarity. I think it's good. We'll move on to the next step. So I'm going to be trying something different than I've done in the past when I'm trying to print my own circuit boards without using just a simple resist pen or sending the boards out to a professional board maker. I've tried unsuccessfully to obtain a suitable laser printable glossy paper, which is a common way of doing this, and the way I've tried doing it in the past, it seems like nobody seems to carry this stuff anymore here where I live, and online I couldn't find any either. So I'm trying this product by Pulsar, their PCB Fab in a Box toner transfer paper. 10 sheets of 8.5 by 11. Print only on the glossy blue side, handle by the edges to prevent fingerprints, keep paper sealed to prevent moisture loss, blah 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 blah. And there aren't any real instructions on it, appears. So you have to go to their website to see the use instructions. But I bought this stuff from DigiKey, and there's their product number, the one ending in ND, and then the manufacturer's number, 50-1101. And there's their website, PCBFX. The actual company's website is pulsarprofx.com, but if you're just dealing with the PCB fab in a box, and they have the shorter URL. So I'm going to read this. Toner transfer paper, or TTP, ideal medium for all laser printers and toner-based copiers to capture and then refuse the image to the copper surface for etching. Toner images print perfectly to the transfer paper because the printer thinks it's a regular soft sheet of paper. However, on one side of the paper is a barrier coating called dextrin that prevents the toner from touching the fibers of the paper. The printed circuit image is then laid face down over the copper and subjected to the high heat and pressure from the toner image applicator, or a calibrated household iron, upon which the toner image will refuse or stick to the copper surface. The board and the paper are then submerged in a tray of water, and the dextrin coating begins to dissolve. Within a minute of being wet, the paper completely releases the toner and floats away from the board on its own. At this point, the board is rinsed under tap water and dried, ready for the application of the green TRF film that will transfer on top of the toner image to seal the image for etching. That wasn't mentioned as being something that was required. I hope I don't actually need that stuff. So they recommend bonding the green TRF foil. Toner is a very porous material. If left alone on the board and etched, you would wind up with micro-pitted copper or even near invisible hairline breaks due to the porosity of the toner. It's just not a solid toner image. The etchant actually gets into the toner and works its way down to the copper, resulting in very poorly etched circuit boards. The green TRF solves this problem completely by encapsulating the toner image in solid plastic color, an absolute must-have for producing high quality. Well, it sounds like if I'm willing to live with something a little less than optimal, I don't need to use that stuff. Okay, I'm gonna try printing to my color printer because my regular desktop laser printer never seems to print as boldly or densely as my color one. But I have a different color printer now than I used to have. I'm not sure if it's going to do an equivalent job. Still, I'm going to try it. So I'm going to select my Hewlett-Packard color laser printer. I'm going to print the bottom copper layer. No silk screens. Paper's going to be in portrait orientation. I don't want to print any footers, or I don't want to print in color. Okay, I have the blue side of the paper up. Feeding it in, and I made sure I checked with the print image on the printer that it's going to print on the top side of the paper. I've got this stupid problem now. This thing always likes to go offline. It's connected by Wi-Fi, and half the time the darn thing wants to go offline. I have to futz with it. That woke it up. Seems like I got a pretty clean image on there. It doesn't seem like it's really lightweight or anything. I don't see any gaps. I'm just going to try it this way. Okay, I'm going to use some really fine sandpaper on this board to clean it up. Okay, I've lightly sanded the board, and I've washed it in lukewarm water with some dish soap, rinsed it off thoroughly, and then dried it with a paper towel, patting more than rubbing, and just letting the rest evaporate, any tiny amounts that are still there. Okay, I have cut the board out or the pattern out just a little bit bigger than the border, and by holding it by the edges, place it on there, try to get it more or less centered, and I just taped it in place with, what's the stuff called? Kapton, I think. It's a specialty tape that's often used for electrical things. I think it should hold up better than something like Scotch tape or just normal masking tape under the heat. And it's very thin, so it doesn't have the thickness of masking tape or something. I recently got a heat press to use for a couple of the organizations I'm with to do some custom t-shirts and things like that. If you make up like the laser printable decals, then this is one of the things you could use to transfer that to fabric. And just based on some information I got off of some online stuff, YouTube videos and so on, it seemed like a lot of people using probably very similar heat presses were doing a good job with temperatures around 280 degrees Fahrenheit, but Pulsar for this blue paper recommends 270 degrees, so I'm going to try that initially. And they don't really specify the amount of time. You should do it by experimentation, but the online information suggests that a lot of people are using 90 seconds. So I turn this on and I push set, and it's set to 360 degrees Fahrenheit. I want to go to 270 degrees, push set again, and go to 90 seconds. Oops. Let's try that again. Okay, so it's supposed to be heating up, and the instructions with this thing are awful, but I don't think it is hot enough until it says it's hot enough, so I'm waiting for the temperature to come up. So it's sneaking up on it. It's starting to modulate the power to the heating element as it gets close. Before it was just on continuously. Waiting to see what it does when it gets up to 270 degrees, if it does. Oop, yep, we're sneaking up on it. Hopefully it beeps or something. No? Well, it seems to be trying to hold it close to 270 degrees. So there's this silicone rubber pad here that can handle the temperature. And I lay my board on here, paper side up, and I think I could just use it the way it is, but a lot of people recommended putting a couple layers of paper towel over it, so I'm going to do that. And I'm going to wang this thing down, and the timer has started timing. Seems to be holding the temperature pretty well. It's cycling the heating element. 40 seconds left to go. Still managing to hold it just shy of 270 degrees. 268, 269 in that area. About 20 seconds. There's apparently two heating elements on here, and it's not cycling them together. It cycles one, leaves the other one on, and so on. Here we go. It should be just about over. Okay. So now I'm going to let it cool off just a little bit. Okay, I have a tray of water here, and I'm just going to I'm not sure if I want to keep that capped on tape on there or not. I forget how long they said I'm supposed to let it lay in there, but I'm going to give it about a minute. I already see an issue right down here. It may be not too easy to see in the video, but there's two pads here for one capacitor and only one pad here for this capacitor. There's like a gap just between the traces and no pad right here at that point, and I think that's just a mistake in my pattern, that I had laid it out and then I'd been experimenting with copying one of the pads to use for some other temporary thing, and I think I inadvertently moved a pad and then deleted it rather than leaving it in place. And even after I gave a quick visual inspection before printing, I missed that, so I don't think there was ever a pad there on the pattern. Well, let's see what happens. It's been waiting a long time now. Seems like it should come off. That came off real easy, no scrubbing or anything. The pattern looks really good, except for that one missing pad that I already identified. And the text did come out correctly. So I'm going to just wipe this a little bit with my microfiber washcloth. I don't think it should need much more than that. Okay. I'm going to use a Sharpie pen to just draw in that pad so I don't have to reprint and redo this whole thing. Well, I've touched up a couple spots, mostly where I had the capped on tape, right over in these areas where I was doing some handling of it. I think in the future I'm going to try to, when I can, in this case the pattern takes up almost the whole available board space, so I couldn't have a lot of extra space. So I think futzing around with it in those areas caused some damage to the toner patterns before they had cooled and really bonded to the copper. So I've just gone around and kind of crudely touched up spots that I could see where there were irregularities in the pattern, kind of sloppily, as you can see there. I'm not very precise, my hands aren't that steady, but I'd rather do this than have to patch it with solder later on. I may still have to do that. I always try to warm my toner a little bit. Oh, it's turned off, duh. So maybe we'll get some action now. Okay, I'm going to pour some ferric chloride in there. Okay, I think that was plenty hot. Let's see. Okay, let's see what happens. Now that my etchant has cooled off a bit, after about a minute of agitation, those light areas around the outside are places where there is no copper left, as you can kind of see there, and the copper that's remaining is very thin. So I usually let it sit until it forms kind of a dark, can't do this with the reflection. It's like my eyes don't see the reflection, but the camera sees everything. It's annoying. And once it gets dark so I can't even see the traces anymore, then I agitate it away to get fresh etchant in those spots. Let it sit for a moment again. Agitate. Nearly there. Okay, I think that's probably about it. I don't really see anything in the background except just some ferric chloride sitting on the board. Let's rinse it off and see. Okay, it's been rinsed. Okay, I'm going to use some acetone to remove the toner traces. Just get a little bit of it on a paper towel and wipe away. Alright, well, you can kind of see it there. It's not perfect. Some etchant did get through in quite a few places. So it's got a very marred, rough, pitted quality to it, more in some places than in others. So even though it stayed intact, I might want to invest in that green film that the guys at Pulsar are recommending. That's supposed to prevent that. But for this one, I think it's probably good enough. There will be enough copper there to do the trick. I might also just drag my soldering iron along those and make a rough and dirty plating job out of it. Text came out pretty good. I actually didn't get all the toner off of one area there. So this was a 0 or 0.04 diameter drill, the smallest one I have in my drill index, and it's not a very good chuck I've got to reduce down to that. It always holds the bit a little bit askew and it wobbles a bit, but it was okay. I've sized up the drill size for the holes that are going to have the wires in them. I need to raise the bed. Mounting holes. I'm going to use a piece of Scotch-Brite Ultra Fine to clean up the board now after drilling. Alright, time to build the board before the copper corrodes just from exposure to the air. So there's the assembled board. Some of the pads didn't solder very well because the holes were so large that there was almost no point of contact between the leads and the pads, and I had to really flood them with solder to get it to make a decent joint. But now I'm going to go and just try to drag solder over all these foils. Then it's going to look like a dog's breakfast, as Dave Jones might say, but some places the foil is kind of thin here due to etchant making its way through the toner. Okay, there's after I've tinned, solder tinned every foil on the board, so it's nice and lumpy, but at least there's a good thickness of conductive material now. Okay, I've got my benchtop AC access panel, which I have a video on, wired up to some clip leads, and those are clipped onto the primary of the transformer, since I don't have any actual wires soldered on there yet. And I'm going to power it on, and got my voltmeter hooked up. Now these trim pots come from the factory set to their mid-range, which is where I made my design calculations from. This is the 1.35 volt supply, and it's 1.38. And this is the 3 volt supply, and it's 2.979. So it's already almost dead nuts on. Okay, I've adjusted it to 1.35 volts. And the other one's been adjusted for 3 volts. Just 2 or 3 turns maximum to get it where I wanted it. That's 2 or 3 turns on the trim pot. I've let this run for about 10 minutes so far. Now granted, there's no load on it, but the heat sinks are absolutely cool. I don't really expect them to have much heat on them with no load though. So tomorrow's project, it's getting too late today, but tomorrow's project is to hook this up in place of the batteries on the IM-25 and see if it does the trick. And assuming it does, then I'm going to mount it to the case and wire it up properly. Okay, I have my battery eliminator just sitting there and hooked up with test clips, and I'm hooked up to my decade resistance box, and so far I'm getting appropriate readings. This should be about 24 ohms. I'm on the ×1 scale, and I'm reading just shy of the half point between 20 and 30 ohms, so that's good. Let's go up to the 10 ohm range, or the ×10 range, and put in about 60 ohms. And as usual, I have to re-zero this almost every time I change anything. Yeah, it's sitting there low, so I have to roll the zero up. So again, it should be 60 ohms, and it's 6, just over 6 ×10, so that's good. Let's bring up 260 ohms, and again, it's sort of in the ballpark. Do a sanity check by zeroing the meter. That's still pretty good. Let's go to the 100 mode, and it's reading just on the high side of between 2 and 3, which times 100 should be the 260 ohms I've got. I can bring in 3K there, so let's just keep life simple. Once again, I've changed the range. I need to make sure I'm still zeroed. It's pretty good. So reading a little high for 3K, but not bad. 7K, I'm way off the board, so let's go up to the ×1000. Once again, I want to check my zero. It's pretty good. So I'm reading about 7K there. That's appropriate. And if I go up to the ×10, it's reading about where you'd expect 7 to be there. And let's bring it up to 57K, and it's a little low on the 6 side, or a little high towards 6 on there, but if I go up to the 100K, it's reading about 6 on there, a little higher than 6, and that's appropriate for 56. So again, it's really close. I would say that this battery eliminator is working just fine, so now all I have to do is mount it properly in the case and make the wiring more permanent. And I've checked during the course of my tests here to make sure that the voltage on these hasn't changed for some reason, and it has not. It's holding where it should be, and this has been running for about 15 minutes now, and boy, I can just barely detect any warmth on the heat sinks. It's just the slightest, barely perceptible warmth. Yep, I think it's working pretty good. Alright, I've peeled the Heathkit label from over here, moved it here. The adhesive was all dried out, so I used a little super glue, just wicking it around the edges, and hit it with accelerant to hold it in place. And then I used mineral spirits to clear up the dried old adhesive. That worked pretty well. Now I've got to find the final position of this guy, which I think will be just about here. I have 4 button head hex drive black anodized 1/4 inch long 440 screws here, and a 3/4 inch long 1/4 inch across 440 tapped, I think it's tapped all the way through, aluminum spacer. So I'm going to cut the middle part of this out and make 2 1/4 inch long spacers. Okay, I've got the 2 spacers screwed into the panel. And there's their couple of screws. And now I've cut down these 2 screws a little bit, make them just a hair shorter. Alright, battery eliminator is mounted, and I'm just going to do one more sanity check with fit into the main meter assembly, and if that all still looks good, then I'm going to put connectors on these wires and do one final test. Alright, I have scraped the solder mask off of the 2 switched leads, hot and neutral. The AC power comes in here on this cable and goes up to this contact and this contact, and then it comes out of those and runs back through these foils and goes up to the primary of the transformer. So I've tacked on a black and white wire. Not that it really matters which one's connected to hot or neutral at this point in the circuit, but I'm just trying to maintain some continuity. So for strain relief, because these foils lift off so very easily, I'm going to do the same thing I did with these other wires and pass them through the board and then hot melt glue them. And in this case, since I'm originating them on the back of the board instead of coming up from the other side, I'm going to go down and then back up through another hole. Okay, there's that. And this one here goes through and then up, and then I've got my short pigtails here. And that's what it looks like from the other side. Got my hot melt glue gun going to put a glob of glue on there, and it should be ready to rock and roll. Okay, here's my sanity check. There's the back of the meter put on. There's looking past the battery holder at the battery eliminator. And there's the other side. Sitting in there pretty nicely. Lots of room around it in case it has to dissipate heat, which it won't. About a 1/2 inch clearance between the transformer and the circuit board, and there's nothing on the circuit board on the other side of that. And it's right in line with the original power transformer. The nearest components are the AC coupling capacitor between circuit ground and chassis ground, or earth ground, which certainly wouldn't be affected by anything, and then the filter capacitor for the power supply, which also could care less. So I think that's an ideal location for this. Okay, I've put a female Molex connector here marked 1.35 volts. The let's see, number 2, which one's which? This is the plug for the main battery, which we won't be using, but it doesn't hurt to have it plugged in. This is the plug for the 3-volt battery, which its corresponding plug was already here. These are ones that were on from my earlier restoration, as was this one, which is the AC power feed, straight from the line cord. It's not switched. Whereas the new one I've added here is on the switched side of the line, and I've got it marked T for transformer. And then the corresponding wire from the battery eliminator is also marked T. And this is a male connector. These are polarized, by the way. They've got that kind of angled end, which is the orientation feature. So that'll go up there. And let's see. So I have the 1.35 volt. And that'll go up to here. And the 3 volt, that is marked 3. And that will go in place of the one from the 3 volt battery that's marked Roman numeral 3, and that'll go up to here. So the only plug which will be unused will be this one from the 3 volt battery. Everything else will be plugged into somewhere. Alright, everything's all plugged together now. Okay, I'm reassembling the side rails with the spacers and the 2 screws. And then the handle slips over that. And then these corner brackets go on. Cover that up. And they get held in place by these big wide flange panhead type screws. Kind of like that. Okay, that's the bottom with everything in place. Still have to tuck the wires away, but I'll do that when I put the top and bottom on. And there's the top side. Again, I need to do some wire tucking before it all goes back in. Kind of like that, probably. I'm going to put on 4 new feet of the same kind that were on it originally, although these are black instead of brown like they would have been. These are 3M bump-on feet. Alright, there's with the bottom put on. Okay, completed. I've put a couple of labels on the back of the unit. This meter has been retrofitted with a dual battery eliminator. No internal batteries are installed. The meter will operate correctly using only AC power, power switch equal line. And the dual test probes provided are intended for VTVMs. On this meter, the red DC probe should only be used only for DC volts. All other functions, AC or DC, must use the black probe. Okay, here is the beauty shot.